This is another WJEC Unit 2 physics question, A-level physics on waves. This time it's question 3 from June 2017 and it's a question about refraction. We've got a wavefront AB about to enter a different medium in which it travels more slowly, and the direction of travel of the wavefront was also shown. I've already completed most of the next part of the question, just simpler to do before I sort of did this in the video form. We need to remember that when the light, or whatever wave it is, travels from the faster medium to the slower medium, the light bends towards the normal. So I've added two rays showing the direction of the wavefront, and I've also drawn the actual wavefront itself, which is at a 90-degree angle to the direction that the wave is shown. You're going to need both of those things there. We're going to need both of these parallel rays here and here, and also this wavefront there. Next we have a diagram showing the path that a ray of light could take through an optical fibre, and this is a multi-mode optical fibre. We're told that for light to travel many meters through the fibre core, the angle theta must not exceed a certain maximum value, theta max. And then we're asked to show that theta max is approximately 8 degrees, given our answer correct to two significant figures. Well, here the key to this is to realise that in this particular diagram, this angle at the top is actually the critical angle. So let's apply the critical angle formula that's given in the WJEC data book, which is n1 sine theta 1, or sine theta c in this case, equals n2. N1 is the refractive index of the material that the light starts in this case 1.52, and N2 is 1.504. If you manage to get those numbers the wrong way round, your calculator will come up with a syntax error. So we can calculate theta c from sine minus 1 of 1.504 over 1.520. We type that into a calculator, making sure that we're in degrees mode, not radians mode. We're going to get an answer of 81.7 degrees. That's not the angle that's marked in the diagram. The angle that's marked in the diagram is this one, but there's a right angle triangle here, so theta is going to simply be 90 minus 81.7. Which to two significant figures gives us 8.3 degrees. Next we have to explain why the fibre wouldn't transmit light efficiently if theta were greater than theta max. Well, if theta was greater than theta max, then the angle of incidence at the boundary between the core and the cladding would be less than the critical angle. And that means total internal reflection doesn't take place. So let's call it TIR for an abbreviation. That means that light will escape into the cladding, each time a reflection takes place. So by the time we get to the end of the fibre, there'll be very little light left. The final part of the question tells us that light takes 1.35 microseconds to travel a certain length L of the fibre by the quickest route, which will be along the axis. We've got to determine how much time, or how much greater the time would be for it to travel the same length of fibre by the zigzag route at an angle theta max to the axis. So if we go back to the diagram, if we call this side AC the straight path and this side AB the zigzag path, we can realise that this angle at the bottom is 8.3 degrees that we calculated earlier. The two sides we have are the adjacent and the hypotenuse, so we can write that cos of 8.3 is S over Z. And that means that the zigzag path is the straight path divided by cos of 8.3. Now, using an unrounded figure here, I get the answer that 1 over cos of 8.3 give me a second, is 1.0106. Excuse me a second. Pen has decided it doesn't want to write anymore, so let's try that again. 1.0106. So what that tells us is that the zigzag path is 1.0106 times longer than the straight path, and because distance and speed are directly proportional, because speed equals distance over time for a constant speed, it means that the time for the zigzag path will actually be 1.0106 times the time for the straight path, or 1.0106 times the 1.35 microseconds that we were given earlier. That will give us that the zigzag path takes 1.364 microseconds, and the time difference, the difference between the zigzag path and the straight path, will be 0.014 microseconds. Thank you for listening. Don't forget to like and subscribe.